Welcome back to the next video, everybody. Today we're going to look at Ribet's theorem. Let's get into it. So first of all, I would highly recommend you watch the previous video on the Hecke on diamond operators on S2n, the weight 2 cusp forms for gamma 1n. If you haven't done so, please do that now. So let's let P be a prime. Let's let T prime of n be Z adjoin T sub L and diamond of D. So this is a subset of the endomorphisms of S2n. It's the Z algebra generated by the Hecke operators T sub L and the diamond operators diamond of D, where L runs over all of the primes not dividing NP, and D runs over all the elements of Z mod NZ cross. Okay, so all of these operators were defined last video. So we're just going to take the Z algebra generated by them, basically. All right, so what's a modular Galois representation? Let's let A be a coefficient ring with residue characteristic P. Okay, we're going to say a Galois representation rho from GQ to GL2 of A is modular of level n and weight 2 if there exists a homomorphism, a ring homomorphism pi from T prime of n to A, such that rho is odd, unramified outside NP, and for every prime L that doesn't divide NP, trace of rho of Frobenius at L is pi of TL, and determinant of rho of Frobenius at L is pi of diamond of L times L. What's going on here is this is analogous to the defining properties of the representation rho sub F, the representation attached to a new form, also defined last video, because there in that theorem, the new forms under consideration were eigenforms for the Hecke operators T sub L for primes L, and the coefficients A sub L of the Q expansion of F were exactly the Hecke eigenvalues of F, the T sub L Hecke eigenvalues of F. And so pi of TL here is just AL in that situation. That's what's going on. You can replace this by AL, and then you get exactly the defining property of one of the defining properties of the Galois representation attached to a new form F in the previous video. And then similarly, the eigenvalue of diamond L is always epsilon of L, where epsilon is the character of F. And so pi of diamond of L should be thought of as epsilon of L here. But once you think of it like that, this is again one of the defining properties of rho sub F from the last video. So you should think of pi basically as having the following property. When you plug into pi one of the Hecke or diamond operators, it like spits out the eigenvalue of some new form. That's loosely how you should think of it. Okay, but we know those eigenvalues are A sub L and epsilon of L respectively. Okay, so I'm going to give you an easier way to think about modular Galois representations right now. Let's let V and W be vector spaces, and let's let G be a group. We'll say that two representations rho from G to aught B, automorphisms of B, and rho prime G from aught W are isomorphic. And in that case, we'll write rho is isomorphic to rho prime if there is an isomorphism of vector spaces, V with W, of course, but such that more is true. We want the following diagram to commute for all G and G. So we have the isomorphism upstairs, V with W. Okay, but then rho of G is a map from V to V for all G and G, right? And rho prime of G is a map from W to W for all G and G. Okay, and then downstairs I have the isomorphism of V with W again, and I just want this square to commute for all G. All right, so once you have this terminology, it's a lot easier to describe what it means for a Galois representation to be modular. We'll say rho is modular of level n and weight 2 if there exists a new form F and S2n such that rho is isomorphic to rho sub F. Okay, so I think that's a lot easier. That's a much easier way of thinking about the modularity of a Galois representation. Okay, the last thing we need to briefly discuss, although I have an entire chapter essentially dedicated to this in my notes, that'll be chapter 7, and a lot of those videos are already up on my channel. That's the notion of Serre's conjecture. Serre's conjecture is now a theorem as of 2008, proved by Carré and Vinton-Berger. But we won't say anything about it as a theorem, just as a conjecture here. So let's let P be prime. Serre conjectured that every odd irreducible Galois representation rho naught from GQ to GL2 of FP bar is modular in the above sense. That is, there's a new form of type, let's say n, level n, weight k character epsilon, such that rho bar F, so the semi-simplification of the reduction of rho F, is just isomorphic to rho 0. Okay, and furthermore, Serre actually gave a prescription for the n, k, and epsilon that should show up. And I'll say a little bit about n and epsilon here. K is a little bit more complicated. Let's let rho from G to GLV be a Galois representation where V is a two-dimensional vector space over FP bar. You can filter G by its so-called L-adic ramification groups, so G0, G1, and so on. So this is where things act trivially mod primes to various powers instead of just mod primes, okay? And then we'll let VI be the subspace of V fixed by G sub I, okay? The conjecture asserts that the level n that should show up in the modularity condition is what we call the Artin conductor of rho. So finally, I'm defining the conductor of representation here after who knows how long. So what is that conductor? It's the product over primes L that aren't P of L to what we call the exponent of the conductor at L, NL rho. I won't give a precise definition for NL rho, but I'll give you some enlightening properties of it right now. First of all, NL rho is always a non-negative integer, and it satisfies two key properties, among others. NL rho is 0 if and only if rho is unramified at L. That's the first one. 2, NL rho is the dimension of V mod V0 if and only if G1 is trivial, i.e. we have a name for this, if and only if rho is what we call tamely ramified at L. So the ramification isn't too bad in some sense. All right, so that's N, it's the conductor of the representation. What is the character epsilon? It's a pretty easy check that to see that if L is a prime not dividing NP, and if frob L is the associated Frobenius element of G, remember this is actually a conjugacy class of elements, then the determinant of frob at L is L to the H times epsilon of L and F P bar star for some H in Z mod P minus 1Z, and some character epsilon from Z mod NZ cross to F P bar star. And this character epsilon is the epsilon from the conjecture. And then, as I said, I won't talk about K here. It's a little bit more complicated, but you can see Sayre's paper, Sayre's conjecture. You know, there's a whole paper from Sayre on his conjecture, which is where this originates. And in fact, there's even an English translation. Okay. So why am I talking about Sayre's conjecture, even though it's not that important in generality for this video? It's because Ribet's theorem, or Ribet's level lowering theorem, if you like, formerly known as the epsilon conjecture, is actually a special case of Sayre's conjecture. And we see how that is in chapter 7 of my notes. So here's the theorem. It says, let F in S2 of gamma 0 NL be a new form where L is a prime that doesn't divide N. Suppose that rho bar F is absolutely irreducible and that one of the following is true. Either rho bar F is unramified at L, or L is P and rho bar F is flat at L. So again, we see flatness taking the place of unramification at the prime P itself. Then there's a new form G in S2 gamma 0 N such that rho bar F is isomorphic to rho bar G. So you can actually take the level of F, which is NL, and you can lower the level from NL to N. That's what's going on. And you have an isomorphism of Galois representations when you do that, provided certain special conditions are satisfied. So for the proof of this, you can see Ribet's paper on modular representations of G Q bar over Q arising from modular forms. We'll call that RMR from here on out if we refer to it again. Okay, just one last remark. It's one of many important consequences of a very, very difficult theorem of Cariol's, which I'll call Cariol's hard theorem from here on out, that if I give you a new form F, the conductor of rho F is actually equal to the conductor of F. Okay. Which is basically God-given in my opinion. So we will use Cariol's hard theorem for a number of other things in this series of talks. And in other talks related to modularity and Fermat's last theorem, I'll give a very brief overview of chapter 20 of Cariol's hard theorem, although it's one of the things about Fermat's last theorem I understand the least about, to be honest, because it's just very difficult. Cariol's paper, I have given the title here if you want to go try to read that very daunting, very long, like 60-page paper in French yourself. The mathematics is very difficult. It would be one of the hardest things you could do for this theorem, even if it was in English. Okay, so it's definitely something maybe that you would consider black boxing, but essentially what Cariol's theorem does is it lets you match up anytime you have two things that are both called the conductor of something or something attached to something. Cariol's hard theorem probably comes in and says that those two conductors are equal. Okay, so next time we will begin looking at the notion of the modularity of an elliptic curve. So I'll see you then, and thanks for watching.